Thank you all for coming. It really is wonderful. I can see that there's a bit of a gap here. Obviously, you've worked out that it's not to being firing line of the speakers is not a good idea here. You're far enough away. It's more than 2 meters. That's fine. It has been an interesting time, and I'm going to just very briefly tell you something about where we've come from and where we hope to be going to and what's happened. And a huge amount of this is down to Sammy for organizing this meeting with Victoria, Nicola, and the rest of my group, and to running the network. And we'll make some comments about running the network turned out to be somewhat different from what we anticipated when we employed Sammy. Let's put it that way. So there's a thing, we've been looking here at, oh no, I guess I have to, oh no, it's okay over there. The screen's, it's more intelligent than I thought. So artificial intelligence, when we bid for this network, I had come across a few things. I didn't put this in the bid presentation for the network. Do think stupid things faster with more energy. I think you can probably think of many examples when new technology comes in of that's the first thing you do. You do things that you could have done much better otherwise, but it's new and it's better to do it all again with some new tool. And the new tool normally is less efficient and more energy consuming and probably doesn't even give you quite the right answer. But it was fun to do. And there's definitely an element of that going on in artificial intelligence. AI has been running for many years. It's gone through many winters. The current incarnation of machine learning, however, is proving to be extremely useful in chemistry and in science in general. So I'm just going to have a brief look through here about some of the things that have gone on here. Now, one of the things is using data-driven ideas, and I'll come back to that in a moment, is all very well, but I've just been teaching this to our fourth year students about correlation is not causation, but it's very clear that chocolate consumption drives Nobel Prizes. I mean, obviously it's true that chocolate. The strange thing is there seems also to be a nonlinear linking between milk consumption and Nobel Prizes, which obviously means it's milk chocolate. And that's probably why Belgium isn't and Switzerland are not quite as high up as you might have thought. But all sorts of issues here, and perhaps it's just an amusing way of looking at the fact that just data-driven stuff doesn't always tell you what's going on, and maybe that's a point we need to think about. But nonetheless, in the last few years, and hopefully we've catalyzed some of this and brought some new people into these ideas, that drug design, that's probably one of the more obvious areas in the pharmaceutical industry that machine learning has made a huge difference. But I think perhaps the biggest revolution is turning out to be in materials design, because the computational complexities in materials are perhaps even more difficult than in the pharmaceutical industry, and so some of the advances machine learning has led to are perhaps even more obvious. I still think if I'm asked what is the next area that's machine learning will have an impact on, it's going to be something like, I think, the complex mixtures, because almost everything you buy, whether it's a food or oil for your car engine or whatever, turns out to be an incredibly complex mixture that a huge amount of experience has gone into in actually working out what's in that mixture. Some of you might have read Primo Levi's books, and the periodic table in particular, and he's working in a paint factory, and there's something that's in there, and nobody knows why it's in there anymore. And it transpires that it was put in place of something else because he couldn't get hold of it during the war, and nobody had remembered why it was there. You could remove it without a problem. There are all sorts of complexities there. But ultimately, we're often the materials are being used to make some sort of device. The potential drug candidates are being used in people. It's actually designing for a purpose, and the machine learning needs to actually really to be useful to include those purposes. And why doesn't it want to? Okay. So one of the things that I've realized as we've been doing this is that we really is a tyranny of chemical space here because it's so large. So what are we trying to do with computational chemistry and machine learning? We're trying to use these to decide what molecules to make, because we only have a limited amount of time. We only have a limited resources, both physically and human. So we want to make more of the right molecules. What the right molecules are depends on your purpose, but we just don't want to randomly make things. So the hope and expectation is we can reduce the number of molecules we need to make by doing some calculations first. That could be pure quantum chemistry calculations. It could be machine learning style. And part of this is because we can conceive of far more molecules than we could possibly ever make, in fact, are possibly makeable. So we really need to do this and choose carefully. But to make good predictions, we need a good model. So we want a good model of what we're trying to make, why we're trying to make it, and using that, we can then hopefully predict some good ones to make. But it needs to be a good model. How do we make a good model? Well, it turns out, especially if you're a machine learning expert, you need a lot of data. If you're a deep learning expert, you need even more data. And if you happen to play games like AlphaGo does, you can play yourself. And you can play yourself to your heart's content, or at least until Google's money runs out, and it can record billions of games. But we're not going to make billions of molecules. But on the other hand, we need billions of molecules to train that sort of network. So we have up this interesting problem. To get the data, we need to make lots of molecules. So in order to work out how to make fewer molecules, we need to make lots of molecules. So we do have a little bit of a problem here, and obviously it isn't as bad as that, but we do have to think carefully about what we're trying to do. And one of our problems is that we don't have a map for chemistry. We keep trying to draw up bits of map of chemical space, and this is one of the big hopes of the data-driven approaches, that we might be able to find a map. And it turns out geography has sort of been there first. It has maps, and one of the ideas of maps is everything is related to everything else, but near things are related to more than distant things. And that does apply when you've got actual geographical maps. And we kind of believe it applies in chemistry. We just have a little bit of a problem. We don't quite know what actually related always means, and we don't really know what distance means, and we keep changing our minds. But part of that, maybe we are making some progress in getting a map. But the map, it's like exploring new places. If we don't have any molecules in that part of the map, we have a bit of a problem. And data-driven approaches do sometimes run into that difficulty. Now, I'm a great believer in following Donald Rumsfeld in all sorts of stuff, just not in any of his political things. But if we do his famous known and unknowns here, with known descriptors, properties, long experience about molecules and how they affect activities, things like log P and so on, affecting whether or not a molecule is ever going to get into a cell. There's a long history in QSAR models. So chemists have been doing this sort of data-led approach, kind of machine learning, for a long time. And I would say QSAR is this known descriptors. We know what we're dealing with. Moving up in his sequence, we have the known unknowns. So we have a load of possible descriptors. We don't really know what's going on, and we try and use our data-driven models to actually learning to supervise this and get somewhere. And then we have cases where we haven't the faintest idea what's going on, but we figure if we throw enough data at a model, it might find a pattern in there. And I think characterize that unknown unknowns as the unsupervised learning. And of course, sometimes we don't even know what we should throw at the computer, but we do know what we want. And what we want is something that predicts something well, and we can put a metric in there of how well we're doing, and that is called reinforcement learning, because the machine basically only knows what you're trying to get out of it at the end, and it has to go away and find as many possible parameters to put in. Actually, it's getting even better than that, because we now have these generative models. So once you've got a model from some sort of random guess, you're no longer filtering out molecules you already know. It actually starts generating molecules that might be useful. And what's even better about that is it can actually tell you whether you can make them or not. And one of the difficulties we have is you might be trying to reach multiple objectives, but you may have the ideal molecule, but if you can't possibly make it, or preferably buy it, then don't bother with that one and move on to the next one. So these generative models are getting really very potential impact. But if you don't build in something useful, like you've got to be able to dispose of your compound, then you're still going to run into trouble. So we still need to think carefully about what it is we want to do. And I'd like to highlight one of the things that came up really from Ross King's contribution to our last network conference, is that we're always in science doing a rather dangerous thing. We're not doing deduction or induction. We're doing abduction. So from a case history of a number of observations, we try and draw out a generality. And there's always a worry that there might be an exception. So in science, we're not doing pure maths usually. So we can't do the pure deduction. And there is always a danger that there's another observation around the corner. And we collect all this data, and we try and draw out a theory. And one of the interesting things is the more data we collect and the more theories we have, the more data we throw away. But it wasn't useless collecting the data. You had to collect the data to get the theory. But once you've got the theory, you perhaps don't need that data anymore. But that can have a slightly adverse public image. So are we going to do data-driven or theory-led? That's kind of the big debate that goes on in a lot of scientific discoveries. And of course, it's really neither one than the other. But do we need to understand our answers? Well, usually in the long term we do, but if you want the next drug now, what should you try next? Just getting a good hint is useful. Do we need theory? Yes, we do need the theory, because the theory allows us to extend our boundary of observations, so we can extrapolate perhaps more reliably with theory than we can with just the data. Do we need to understand the theory? Well, I'm just reading a book about the fact, again, that nobody really understands quantum theory. And there are a lot of arguments that have been raging for 100 years, almost, on that. So we have a very effective theory that we can use very well, but almost nobody. There are people who claim they understand it, but mostly we don't. And yet, it's very successful. But it would be best to really understand what we're doing. But through the network, what have we discovered are some of the barriers to actually employing these machine learning techniques? Well, the biggest one that comes up every time is data. Not enough quality data. Not enough molecules have been made. Not enough measurements have been made. So hand in hand with the actual machine learning side of things, we need better ways of making very small amounts of molecules, and certainly much better ways of characterizing small amounts of molecules, so we can afford to make lots to get the data, and then put that data in a form that other people can actually use, which means to the machine learning computer scientists, please don't drop off the units and the metadata that goes with the column of data that we nicely sent you, because the next person won't be able to add to it. Your model should take in quantities, not numbers. And that's where we need the standards to make sure that we do convey the data accurately. And of course, there are standards. And we need standards for the data, and we need standards for the models. And this is a very tricky process, getting agreement on those. And in a fast-moving environment of machine learning work, this is a real problem. But we've been collecting up lots of people. Our membership has been rising considerably over time. This is the membership via our mailing lists and via our Twitter feeds. COVID actually was very favorable for us in that we've reached a much wider audience than we ever could, because we moved online. And we've been very pleased to bring in a good mixture of academics, industrialists, some venture capitalists, students, chemists, material scientists, computer scientists, mathematicians. And as a result, we have a really busy YouTube channel. I'm sure most of you have seen it. It will get even busier after this set of talks. No, John, you've fallen off the top there. You normally, because you gave the first talk, you're normally on there. But obviously, Failed It to Nailed It, our co-series with the Physical Sciences Data Service, is popular there at the moment. One of the things you can see is that it's not just us getting popular. Recently, the survey of numbers of papers in chemistry and physics, material science, you've seen the huge uplift in using machine learning, some of which perhaps shouldn't have used machine learning. But as I said, it was always interesting for them to do it. But we do also see some of the other problems. If you build models you don't understand, you don't really know what the limitations might be, what bias there might be in there. Now, we may appear not to have the sort of classic problem of identifying faces, when it turned out the algorithms would not identify anything other than a white face, because it had not been trained on anything other than a white face. But there are subtle problems in what data you put in, even in something as pure as chemistry. So always got to be aware of the problems of bias. And the future of chemistry being a computational operation before you go into the laboratory has been foreseen by a famous science fiction writer from back to the 1950s. We are getting much closer to it, but you still need to make the molecules. Now, whether those molecules are made by a remote laboratory can be done. Do we think that's really going to be the way most chemistry goes? I'm not sure, but there's certainly a lot more computation, data analysis work going on to parallel the synthesis. And this does mean there's a continuing change in the culture of what chemistry. What does it actually mean? What does it mean to be a chemist? But we're not completely digital chemists yet. We're still in a liminal period. There's a lot of transitions going on. We're only beginning to change what the chemistry education system actually will be. And we need to change it a lot more soon if quantum computers do actually deliver on some of the results that they might deliver for chemistry. So should students give up doing traditional chemistry? Should we stop just basically, we stop teaching them any facts because they look up in Google, but they do have to actually know which is the right one. But maybe we don't need to teach them the same things. Well, Derek Lowe here, I'm sorry that because I clipped this, you may not be able to read it. Have a look at his latest thing or very recent one in Chemistry World in Pipeline, talking about actually whether or not drug discovery, new proteins will all be basically AlphaFold 2 and so on. And he figures actually absolutely not. It's still going to be the people who need to understand what's going on. and that's why you need the understanding of the models. He's quite a persuasive argument there to say the machine learning and the artificial intelligence is going to be useful, but it's not, he thinks, going to do it all on its own. And it's a partnership, which is one of the reasons why our network is the augmented intelligence. But I'm not so sure. Will an AI win chemistry Nobel Prize? Well, it may not win a chemistry Nobel Prize. It may win the equivalent for computer science. Blockchain, or Bitcoin. Blockchain, there is supposedly a person invented this. And we don't actually know who this person is. There's a name, but nobody's identified this person. Perhaps it isn't a person. Perhaps it was an AI. And it certainly must be in the running for an economics Nobel Prize or something similar. So maybe you'll soon see that an artificial intelligence actually does win the equivalent of a Nobel Prize. But it's not going to solve everything. We know that the mathematics behind this, computation, cannot solve every problem. This is Gödel, Turing, Church. There are problems that are not solvable by simple computation. And actually one of the interesting problems about whether or not something is going to be a conductor or not, to do with the band gap as you make molecules longer, turns out to be one of these non-computable things. That doesn't mean it's not soluble, but it means it needs, or has needed, a human mind to get at it. Now, so that's assuming that the sort of machine learning stuff is limited by the classical Turing-type computation. And it may well be, but on the other hand, go back to the fact that we don't understand quantum mechanics. Just because you don't understand something doesn't mean you can't come up with some theorems that tell you that why you don't understand it and what you need to understand. And that was Bell's theorem. I recommend reading about it if you haven't come across it. And whilst there are all sorts of existence proofs for machine learning, I do wonder if somewhere under there's a Bell's theorem for machine learning that we should be using to test all these models with. But we do need to do things. There are rather serious problems. The latest climate report from the United Nations is basically damning. We're already beyond fixing things. So we really need a little bit more work going on there. Otherwise, we are going to go the dinosaurs, which apparently the asteroid hit in around March, sometime that time. Read the Nature paper, I think it is. So watch out. But what's really nice is that we have at least, although we're a hybrid here, and I'm hoping that's working all right, we've actually got some people in the room, and it is nice for me to really use this New Yorker cartoon and say, it's really nice to see you all. Thanks very much.